Hi, my name is Justine Harkness, and in this video, we'll look at how to draw the resonance forms created by a meta-directing substituent. Whenever we need to consider directing effects, we must be looking at a substituted benzene or a benzene ring in which we already have at least one substituent on the ring. Here, this X can denote any substituent. The substituent that is already attached to the ring will influence where the next electrophile will bind. Some substituents will direct that electrophile to the meta position, and that's what we term a meta-directing substituent, while other substituents will direct our new electrophile to the ortho and para positions, and those are what we term ortho and para directors, which we'll cover in later videos. One of the hallmarks of specifically meta-directing substituents, which we are showing here at the bottom of this little table, is that if we look at the atom that is directly attached to the ring, it will have some bit of a partial positive or full positive charge. If we look at one of our weakly meta-directing substituents, our aldehyde, notice that the aldehyde contains a carbonyl, and carbonyls are polar, where we have partial negative charges on our oxygen and partial positive charges on that carbonyl carbon. In fact, if we draw out some of the resonance forms that we can get, we actually have a full positive charge on that carbonyl carbon, which makes it a meta-director. Now, as we go down this table, we get better and better meta-directors because we get more and more positive charge on the attached atom. And in fact, if we look at the nitro group, which is one of the best meta-directors, it has a full positive charge on it. So overall, to recognize a meta-directing substituent, you want to look for some positive charge on the atom that is directly attached to our benzene ring, which here we have denoted just with R. If we consider the mechanism for electrophilic aromatic substitution, we'll be starting with, of course, our benzene ring, which is not overly reactive. So we use an electrophile. Electrophiles are electron-seeking groups. So the more concentrated negative charge we have on the benzene, the more the electrophile is going to want to add to that ring. Now, meta-directors, because of that positive charge or partial positive charge on the atom bound to our aromatic ring, can actually resonate with the ring. It can put that positive charge onto the ortho and para carbons. That partial positive charge that we add to the ortho and para positions will actually repel the electrophile. It makes it less likely to attack those positions. As a result, the electrophile is going to be binding to that meta position, which doesn't have that extra partial positive charge. So let's take a look at the resonance forms created by a meta-directing substituent. So here we have a carboxylic acid group attached to our benzene ring. Now, carboxylic acids are meta-directors, and so if we look at the carbon that's directly attached to the ring, it is attached to two oxygens, which are very electronegative, which would give it a partial positive charge. Now here we need to draw the resonance forms of this particular molecule. Remember that when we're drawing resonance forms, we can move lone pairs of electrons and we can also move pi bonds. So to draw our first resonance structure, we can have one of our pi bonds from our benzene ring move up to this position, and that would also displace the carbonyl pi bond, pushing it up onto the oxygen. What this does is to create a negative charge on the oxygen and also adds a positive charge on the ortho position. So now we have ortho with a positive charge. We can also start moving around our pi bonds within that benzene ring. So when we move our bond, we now have a positive charge at the para position. So para is now positive, and finally moving around our other pi bond, we can get a positive charge on that other ortho position. So if we look at our overall resonance hybrid, to which all of these resonance forms will contribute, what we see is we have positive charge density on those ortho and para positions. Recall that for electrophilic aromatic substitution, we have an electrophile which will attack the benzene ring. Electrophiles want to add to regions of negative charge. So these partial positive charges on the ortho and para position will essentially block the addition of the electrophile to those positions. The positions that lack positive charge would be our meta positions. So the electrophile would add to those positions. So this is why meta directors direct to the meta position. It all boils down to the resonance. So as you are looking at your meta directors, definitely spend some time drawing out the resonance forms for them, since that will really help to solidify this in your mind.